Glass is an amorphous solid material that exhibits a glass transition, which is the reversible transition in amorphous materials from a hard and relatively brittle state into a molten or rubber-like state. Glasses are typically brittle and can be optically transparent. The most familiar type of glass is soda-lime glass, which is composed of about 75% silicon dioxide, sodium oxide from sodium carbonate, lime, and several minor additives. The term glass is often used to refer only to this specific material. Silicate glass generally has the property of being transparent. Because of this, it has many applications. One of its primary uses is as a building material, traditionally as small panes set into window openings and walls, but in the 20th century often as the major cladding material of many large buildings. Because glass can be formed or molded into any shape, and also because it is a sterile product, it has been traditionally used for vessels, bowls, vases, bottles, jars and glasses. In its most solid forms it has also been used for paperweights, marbles, and beads. Glass is both reflective and refractive of light, and these qualities can be enhanced by cutting and polishing to make optical lenses, prisms and fine glassware. Glass can be colored by adding metallic salts, and can also be painted. These qualities have led to the extensive use of glass in the manufacturing of art objects and in particular, stained glass windows. Although brittle, glass is extremely durable, and many examples of glass fragments exist from early glass-making cultures. In science, the term glass is defined in a broader sense, encompassing every solid that possesses a non-crystalline structure and exhibits a glass transition when heated towards the liquid state. These sorts of glasses can be made of quite different kinds of materials, metallic alloys, ionic melts, aqueous solutions, molecular liquids, and polymers. For many applications polymer glasses are a lighter alternative to traditional silica glasses. Silicate glass, ingredients. Silica is a common fundamental constituent of glass. In nature, vitrification of quartz occurs when lightning strikes sand, forming hollow, branching root-like structures called fulgurate. While fused quartz is used for some special applications, it is not very common due to its high glass transition temperature of over 1200 °C. Normally, other substances are added to simplify processing. One is sodium carbonate, which lowers the glass transition temperature. However, the soda makes the glass water-soluble, which is usually undesirable, so lime, some magnesium oxide and aluminium oxide are added to provide for a better chemical durability. The resulting glass contains about 70 to 74% silica by weight and is called a soda-lime glass. Soda-lime glasses account for about 90% of manufactured glass. Most common glass contains other ingredients to change its properties. Lead glass or flint glass is more brilliant because the increased refractive index causes noticeably more specular reflection and increased optical dispersion. Adding barium also increases the refractive index. Thorium oxide gives glass a high refractive index and low dispersion and was formerly used in producing high-quality lenses, but due to its radioactivity has been replaced by lanthanum oxide in modern eyeglasses. Iron can be incorporated into glass to absorb infrared energy, for example in heat-absorbing filters for movie projectors, while cerium, oxide can be used for glass that absorbs UV wavelengths. The following is a list of the more common types of silicate glasses, and their ingredients, properties, and applications. Fused silica glass, vitreous silica glass, silica. Has very low thermal expansion, is very hard and resists high temperatures. It is also the most resistant against weathering. It is used for high-temperature applications such as furnace tubes, melting crucibles, etc. Soda-lime silica glass, window glass, silica 72% plus sodium oxide 14.2% plus magnesia 2.5% plus lime 10.0% plus alumina 0.6%. Is transparent, easily formed and most suitable for window glass. It has a high thermal expansion and poor resistance to heat. Used for windows, containers, light bulbs, tableware. Sodium borosilicate glass, Pyrex, silica 81% plus boric oxide 12% plus soda 4.5% plus alumina 2.0%. Stands heat expansion much better than window glass. Used for chemical glassware, cooking glass, car headlamps, etc. Borosilicate glasses have as main constituents silica and boron oxide. They have fairly low coefficients of thermal expansion, making them more dimensionally stable. The lower CTE also makes them less subject to stress caused by thermal expansion, thus less vulnerable to cracking from thermal shock. They are commonly used for reagent bottles, optical components and household cookware. Lead oxide glass, crystal glass, silica 59% plus soda 2.0% plus lead oxide 25% plus potassium oxide 12% plus alumina 0.4% plus zinc oxide 1.5%. Has a high refractive index, making the look of glassware more brilliant. It also has a high elasticity, making glass wearing. It is also more workable in the factory, but cannot stand heating very well. Aluminosilicate glass, silica 57% plus alumina 16% plus boric oxide 4.0% plus barium oxide 6.0% plus magnesia 7.0% plus lime 10%. Extensively used for fiberglass, used for making glass-reinforced plastics. Also for halogen bulb glass. Oxide glass, alumina 90% plus germanium oxide 10%. Extremely clear glass, used for fiber optic waveguides and communication networks. Light loses only 5% of its intensity through 1 km of glass fiber. Another common glass ingredient is cullet. The recycled glass saves on raw materials and energy. Impurities in the cullet can lead to product and equipment failure. Thinning agents such as sodium sulfate, sodium chloride, or antimony oxide may be added to reduce the number of air bubbles in the glass mixture. Glass batch calculation is the method by which the correct raw material mixture is determined to achieve the desired glass composition. Physical properties. Optical properties. Glass is in widespread use largely due to the production of glass compositions that are transparent to visible light. In contrast, polycrystalline materials do not generally transmit visible light. The individual crystallites may be transparent, but their facets reflect or scatter light resulting in diffuse reflection. Glass does not contain the internal subdivisions associated with grain boundaries in polycrystals and hence does not scatter light in the same manner as a polycrystalline material. The surface of a glass is often smooth since during glass formation the molecules of the supercooled liquid are not forced to dispose in rigid crystal geometries and can follow surface tension, which imposes a microscopically smooth surface. These properties, which give glass its clearness, can be retained even if glass is partially light-absorbing that is, colored. Glass has the ability to refract, reflect, and transmit light following geometrical optics, without scattering it. It is used in the manufacture of lenses and windows. Common glass has a refraction index around 1.5. According to Fresnel equations, the reflectivity of a sheet of glass is about 4% per surface, and the transmissivity of one element is about 90%. Glass also finds application in optoelectronics, for example, for light-transmitting optical fibers. Other properties. In the process of manufacture, silicate glass can be poured, formed, extruded and molded into forms ranging from flat sheets to highly intricate shapes. The finished product is brittle and will fracture, unless laminated or specially treated, but is extremely durable under most conditions. It erodes very slowly and can withstand the action of water. It is resilient to chemical attack and is an ideal material for the manufacture of containers for foodstuffs and most chemicals. Contemporary production. Following the glass batch preparation and mixing, the raw materials are transported to the furnace. Soda-lime glass for mass production is melted in gas-fired units. Smaller-scale furnaces for specialty glasses include electric melters, pot furnaces, and date tanks. After melting, homogenization and refining, the glass is formed. Flat glass for windows and similar applications is formed by the float glass process, developed between 1953 and 1957 by Sir Alistair Pilkington and Kenneth Bickerstaff of the UK's Pilkington Brothers, who created a continuous ribbon of glass using a molten tin bath on which the molten glass flows unhindered under the influence of gravity. The top surface of the glass is subjected to nitrogen under pressure to obtain a polished finish. Container glass for common bottles and jars is formed by blowing and pressing methods. Further glass forming techniques are summarized in the table glass forming techniques. Once the desired form is obtained, glass is usually annealed for the removal of stresses. Surface treatments, coatings or lamination may follow to improve the chemical durability, strength, or optical properties. Color. Color in glass may be obtained by addition of electrically charged ions that are homogeneously distributed, and by precipitation of finely dispersed particles. Ordinary soda-lime glass appears colorless to the naked eye when it is thin, although iron, oxide impurities of up to 0.1 Wt% produce a green tint, which can be viewed in thick pieces or with the aid of scientific instruments. Further FeO and CO2O3 additions may be used for the production of green bottles. Sulfur, together with carbon and iron salts, is used to form iron polysulfides and produce amber glass ranging from yellowish to almost black. A glass melt can also acquire an amber color from a reducing combustion atmosphere. Manganese dioxide can be added in small amounts to remove the green tint given by iron, oxide. When used in art glass or studio glass, glass is colored using closely guarded recipes that involve specific combinations of metal oxides, melting temperatures and cook times. Most colored glass used in the art market is manufactured in volume by vendors who serve this market, although there are some glass makers with the ability to make their own color from raw materials. History of silicate glass. The term glass developed in the late Roman Empire. It was in the Roman glassmaking center at Trier, now in modern Germany, that the late Latin term gelsum originated, probably from a Germanic word for a transparent, lustrous substance. Naturally occurring glass, especially the volcanic glass obsidian, has been used by many Stone Age societies across the globe for the production of sharp cutting tools and, due to its limited source areas, was extensively traded. But in general, archaeological evidence suggests that the first true glass was made in coastal North Syria, Mesopotamia or ancient Egypt. The earliest known glass objects, of the mid-3rd millennium BCE, were beads, perhaps initially created as accidental byproducts of metalworking or during the production of faience, a pre-glass vitreous material made by a process similar to glazing. Glass remained a luxury material, and the disasters that overtook late Bronze Age civilization seem to have brought glass making to a halt. Indigenous development of glass technology in South Asia may have begun in 1730 BCE. In ancient China, though, glassmaking seems to have a late start, compared to ceramics and metalwork. In the Roman Empire, glass objects have been recovered across the Roman Empire in domestic, industrial and funerary contexts. Glass was used extensively during the Middle Ages. Anglo-Saxon glass has been found across England during archaeological excavations of both settlement and cemetery sites. Glass in the Anglo-Saxon period was used in the manufacture of a range of objects including vessels, beads, windows, and was also used in jewelry. From the 10th century onwards, glass was employed in stained glass windows of churches and cathedrals, with famous examples at Chartres Cathedral and the Basilica of St. Denis. By the 14th century, architects were designing buildings with walls of stained glass such as St. Chapel, Paris, and the East End of Gloucester Cathedral. Stained glass had a major revival with Gothic Revival architecture in the 19th century. With the Renaissance, and a change in architectural style, the use of large stained glass windows became less prevalent. The use of domestic stained glass increased until most substantial houses had glass windows. These were initially small panes leaded together, but with the changes in technology, glass would be manufactured relatively cheaply in increasingly larger sheets. This led to larger window panes, and, in the 20th century, to much larger windows in ordinary domestic and commercial buildings. In the 20th century, new types of glass such as laminated glass, Reinforced glass and glass bricks have increased the use of glass as a building material and resulted in new applications of glass. Multi-story buildings are frequently constructed with curtain walls made almost entirely of glass. Similarly, laminated glass has been widely applied to vehicles for windscreens. While glass containers have always been used for storage and are valued for their hygienic properties, glass has been utilized increasingly in industry. Optical glass for spectacles has been used since the late Middle Ages. The production of lenses has become increasingly proficient, aiding astronomers as well as having other application in medicine and science. Glass is also employed as the aperture cover in many solar energy systems. From the 19th century, there was a revival in many ancient glass-making techniques including Cameo Glass, achieved for the first time since the Roman Empire and initially mostly used for pieces in a neoclassical style. The Art Nouveau movement made great use of glass, with Rena copyright Lalique, a Permel Gala copyright, and Dorm of Nancy producing colored vases and similar pieces, often in Cameo Glass, and also using luster techniques. Louis Comfort Tiffany in America specialized in stained glass, both secular and religious, and his famous lamps. The early 20th century saw the large-scale factory production of glass art by firms such as Waterfords and Lalique. From about 1960 onwards there have been an increasing number of small studios hand-producing glass artworks, and glass artists began to class themselves as in effect sculptors working in glass, and their works as part fine arts. In the 21st century, scientists observing the properties of ancient stained glass windows, in which suspended nanoparticles prevent UV light from causing chemical reactions that change image colors, are developing photographic techniques that use similar stained glass to capture true color images of Mars for the 2019 ESA Mars rover mission. Chronology of advances in architectural glass, 1226 a Euro broadsheet first produced in Sussex, 1330 a Euro crown glass first produced in Rouen, France. Broadsheet also produced. Both were also supplied for export, 1620 a Euro blown plate first produced in London. Used for mirrors and coach plates. 1678 a Euro crown glass first produced in London. This process dominated until the 19th century, 1843 a Euro an early form of float glass invented by Henry Bessemer, pouring glass onto liquid tin. Expensive and not a commercial success. 1888 a Euro machine-rolled glass introduced allowing patterns to be introduced, 1898 a Euro wired cast glass invented by Pilkington for use where safety or security was an issue. 1959 a Euro float glass launched in UK. Invented by Sir Alistair Pilkington. Other types of glass, new chemical glass compositions or new treatment techniques can be initially investigated in small-scale laboratory experiments. The raw materials for laboratory-scale glass melts are often different from those used in mass production because the cost factor has a low priority. In the laboratory mostly pure chemicals are used. Care must be taken that the raw materials have not reacted with moisture or other chemicals in the environment, or that the impurities are quantified. Evaporation losses during glass melting should be considered during the selection of the raw materials, for example, sodium selenite may be preferred over easily evaporating CO2. Also, more readily reacting raw materials may be preferred over relatively inert ones, such as Al, OH, 3 over Al2O3. Usually, the melts are carried out in platinum crucibles to reduce contamination from the crucible material. Glass homogeneity is achieved by homogenizing the raw materials mixture, by stirring the melt, and by crashing and remelting the first melt. The obtained glass is usually annealed to prevent breakage during processing. To make glass from materials with poor glass-forming tendencies, novel techniques are used to increase cooling rate, or reduce crystal nucleation triggers. Examples of these techniques include aerodynamic levitation, splat quenching and roller quenching. Network glasses. Some glasses that do not include silica as a major constituent may have physico-chemical properties useful for their application in fiber optics and other specialized technical applications. These include fluoride glasses, aluminosilicates, phosphate glasses, borate glasses, and chalcogenide glasses. There are three classes of components for oxide glasses: network formers, intermediates, and modifiers. The network formers form a highly cross-linked network of chemical bonds. The intermediates can act as both network formers and modifiers, according to the glass composition. The modifiers alter the network structure. They are usually present as ions, compensated by nearby non-bridging oxygen atoms, bound by one covalent bond to the glass network and holding one negative charge to compensate for the positive ion nearby. Some elements can play multiple roles. For example, lead can act both as a network former, or as a modifier. The presence of non-bridging oxygens lowers the relative number of strong bonds in the material and disrupts the network, decreasing the viscosity of the melt and lowering the melting temperature. The alkali metal ions are small and mobile. Their presence in glass allows a degree of electrical conductivity, especially in molten state or at high temperature. Their mobility decreases the chemical resistance of the glass, allowing leaching by water and facilitating corrosion. Alkaline earth ions, with their two positive charges and requirement for two non-bridging oxygen ions to compensate for their charge, are much less mobile themselves and also hinder diffusion of other ions, especially the alkalis. The most common commercial glasses contain both alkali and alkaline earth ions, for easier processing and satisfying corrosion resistance. Corrosion resistance of glass can be achieved by dealkalization, removal of the alkali ions from the glass surface by reaction with, for example, sulfur or fluorine compounds. Presence of alkaline metal ions has also detrimental effect to the loss tangent of the glass, and to its electrical resistance. Glasses for electronics have to take this in account. Addition of lead, 2, oxide lowers melting point, lowers viscosity of the melt, and increases refractive index. Lead oxide also facilitates solubility of other metal oxides and is used in colored glasses. The viscosity decrease of lead glass melt is very significant. This allows easier removal of bubbles and working at lower temperatures, hence its frequent use as an additive in vitreous enamels and glass solders. The high ionic radius of the Pb2+ ion renders it highly immobile in the matrix and hinders the movement of other ions. Lead glasses therefore have high electrical resistance, about 2 orders of magnitude higher than soda-lime glass. For more details, see lead glass. Addition of fluorine lowers the dielectric constant of glass. Fluorine is highly electronegative and attracts the electrons in the lattice, lowering the polarizability of the material. Such silicon dioxide fluoride is used in manufacture of integrated circuits as an insulator. High levels of fluorine doping led to formation of volatile CF2O, and such glass is then thermally unstable. Stable layers were achieved with dielectric constant down to about 3.5 3.7. Amorphous metals. In the past, small batches of amorphous metals with high surface area configurations have been produced through the implementation of extremely rapid rates of cooling. This was initially termed splat cooling by doctoral student W. Clement at Caltech, who showed that cooling rates on the order of millions of degrees per second is sufficient to impede the formation of crystals, and the metallic atoms become locked into a glassy state. Amorphous metal wires have been produced by sputtering molten metal onto a spinning metal disc. More recently, a number of alloys have been produced in layers with thickness exceeding 1 mm. These are known as bulk metallic glasses. Liquid Metal Technologies sell a number of zirconium-based BMGs. Batches of amorphous steel have also been produced that demonstrate mechanical properties far exceeding those found in conventional steel alloys. In 2004, NIST researchers presented evidence that an isotropic non-crystalline metallic phase could be grown from the melt. This phase is the first phase, or primary phase, to form in the alpha-C system during rapid cooling. Interestingly, experimental evidence indicates that this phase forms by a first-order transition. Transmission electron microscopy images show that the Q-glass nucleates from the melt as discrete particles, which grow spherically with a uniform growth rate in all directions. The diffraction pattern shows it to be an isotropic glassy phase. Yet there is a nucleation barrier, which implies an interfacial discontinuity between the glass and the melt. Electrolytes. Electrolytes or molten salts are mixtures of different ions. In a mixture of 3 or more ionic species of dissimilar size and shape, crystallization can be so difficult that the liquid can easily be supercooled into a glass. The best studied example is Ca 0.4 K 0.6, NO3, 1.4. Aqueous solutions. Some aqueous solutions can be supercooled into a glassy state, for instance LiCl, RH2O in the composition range 4, are less than 8. Molecular liquids. A molecular liquid is composed of molecules that do not form a covalent network but interact only through weak van der Waals forces or through transient hydrogen bonds. Many molecular liquids can be supercooled into a glass. Some are excellent glass formers that normally do not crystallize. A widely known example is sugar glass. Under extremes of pressure and temperature, solids may exhibit large structural and physical changes that can lead to polymorphic phase transitions. In 2006, Italian scientists created an amorphous phase of carbon dioxide using extreme pressure. The substance was named amorphous carbonia, a CO2, and exhibits an atomic structure resembling that of silica. Polymers. Important polymer glasses include amorphous and glassy pharmaceutical compounds. These are useful because the solubility of the compound is greatly increased when it is amorphous compared to the same crystalline composition. Many emerging pharmaceuticals are practically insoluble in their crystalline forms. Colloidal glasses. Concentrated colloidal suspensions may exhibit a distinct glass transition as function of particle concentration or density. Glass ceramics. Glass ceramic materials share many properties with both non-crystalline glass and crystalline ceramics. They are formed as a glass, and then partially crystallize by heat treatment. For example, the microstructure of whiteware ceramics frequently contains both amorphous and crystalline phases. Crystalline grains are often embedded within a non-crystalline intergranular phase of grain boundaries. When applied to whiteware ceramics, vitreous means the material has an extremely low permeability to liquids, often but not always water, when determined by a specified test regime. The term mainly refers to a mix of lithium and aluminosilicates that yields an array of materials with interesting thermomechanical properties. The most commercially important of these have the distinction of being impervious to thermal shock. Thus, glass ceramics have become extremely useful for countertop cooking. The negative thermal expansion coefficient of the crystalline ceramic phase can be balanced with the positive CTE of the glassy phase. At a certain point, the glass ceramic has a net CTE near zero. This type of glass ceramic exhibits excellent mechanical properties and can sustain repeated and quick temperature changes up to 1000 AA degrees Celsius. Structure. As in other amorphous solids, the atomic structure of a glass lacks any long-range translational periodicity. However, due to chemical bonding characteristics, glasses do possess a high degree of short-range order with respect to local atomic polyhedra. Formation from a supercooled liquid. In physics, the standard definition of a glass is a solid formed by rapid melt quenching. However, the term glass is often used to describe any amorphous solid that exhibits a glass transition temperature Tg. If the cooling is sufficiently rapid, then crystallization is prevented and instead the disordered atomic configuration of the supercooled liquid is frozen into the solid state at Tg. The tendency for a material to form a glass while quenched is called glass forming ability. This ability can be predicted by the rigidity theory. Generally, the structure of a glass exists in a metastable state with respect to its crystalline form, although in certain circumstances, for example in atactic polymers, there is no crystalline analog of the amorphous phase. Some people consider glass to be a liquid due to its lack of a first-order phase transition where certain thermodynamic variables such as volume, entropy and enthalpy are discontinuous through the glass transition range. However, the glass transition may be described as analogous to a second-order phase transition where the intensive thermodynamic variables such as the thermal expansivity and heat capacity are discontinuous. Despite this, The equilibrium theory of phase transformations does not entirely hold for glass, and hence the glass transition cannot be classed as one of the classical equilibrium phase transformations in solids. Glass is an amorphous solid. It exhibits an atomic structure close to that observed in the supercooled liquid phase but displays all the mechanical properties of a solid. The notion that glass flows to an appreciable extent over extended periods of time is not supported by empirical research or theoretical analysis. Laboratory measurements of room temperature glass flow do show a motion consistent with a material viscosity on the order of 1017 euro 1018 pascals s. Although the atomic structure of glass shares characteristics of the structure in a supercooled liquid, glass tends to behave as a solid below its glass transition temperature. A supercooled liquid behaves as a liquid, but it is below the freezing point of the material, and in some cases will crystallize almost instantly if a crystal is added as a core. The change in heat capacity at a glass transition and a melting transition of comparable materials are typically of the same order of magnitude, indicating that the change in active degrees of freedom is comparable as well. Both in a glass and in a crystal it is mostly only the vibrational degrees of freedom that remain active, whereas rotational and translational motion is arrested. This helps to explain why both crystalline and non-crystalline solids exhibit rigidity on most experimental time scales. Behavior of antique glass. The observation that old windows are sometimes found to be thicker at the bottom than at the top is often offered as supporting evidence for the view that glass flows over a time scale of centuries, the assumption being that the glass was once uniform but has flowed to its new shape, which is a property of liquid. However, this assumption is incorrect. Once solidified, glass stops flowing. The reason for the observation is that in the past, when panes of glass were commonly made by glass blowers, the technique used was to spin molten glass so as to create a round, mostly flat and even plate. This plate was then cut to fit a window. The pieces were not, however, absolutely flat. The edges of the disc became a different thickness as the glass spun. When installed in a window frame, the glass would be placed with a thicker side down both for the sake of stability and to prevent water accumulating in the lead cames at the bottom of the window. Occasionally such glass has been found thinner side down or thicker on either side of the window's edge. Mass production of glass window panes in the early 20th century caused a similar effect. In glass factories, molten glass was poured onto a large cooling table and allowed to spread. The resulting glass is thicker at the location of the pour, located at the center of the large sheet. These sheets were cut into smaller window panes with non-uniform thickness, typically with the location of the pour centered in one of the panes for decorative effect. Modern glass intended for windows is produced as float glass and is very uniform in thickness. Several other points can be considered that contradict the cathedral glass flow theory. Writing in the American Journal of Physics, materials engineer Edgar D. Zanotto states, the predicted relaxation time for GO2 at room temperature is 1032 years. Hence, the relaxation period of cathedral glasses would be even longer. If medieval glass has flowed perceptibly, then ancient Roman and Egyptian objects should have flowed proportionately more euro, but this is not observed. Similarly, prehistoric obsidian blades should have lost their edge. This is not observed either. If glass flows at a rate that allows changes to be seen with the naked eye after centuries, then the effect should be noticeable in antique telescopes. Any slight deformation in the antique telescopic lenses would lead to a dramatic decrease in optical performance, a phenomenon that is not observed. There are many examples of centuries-old glass shelving that is not bent, even though it is under much higher stress from gravitational loads than vertical window glass. The above does not apply to materials that have a glass transition temperature close to room temperature, such as certain plastics used in daily life like polystyrene and polypropylene. Gallery. See also. References. Further reading, Carboni, Stefano and Whitehouse, David. Glass of the Sultans. New York, The Metropolitan Museum of Art. ISBN A0870999869. Osh, Amalananda. An Encyclopedia of Indian Archaeology. Brill ISBN A90-04-09262-5. Jowlett, J. High Definition Archaeology, Threads Through the Past. Routledge. ISBN A0-415-18429-0. Noel C. Stokes. The Glass and Glazing Handbook. Standards Australia. SAAHB 125 Euro 1998, Staff. Robot speeds up glass development. Fraunhofer Institute. Retrieved December 10, 2011. Stuckey, D. Donald. Explorations in Glass, An Autobiography. Wiley, 2000. ISBN 978-1-57498-124-7, Vogel, Werner. Chemistry of Glass. Wiley, 1985. ISBN 978-0-916094-73-7. External links, All About Glass from the Corning Museum of Glass, a collection of articles, multimedia, and virtual books all about glass, including the Glass Dictionary. Glass Encyclopedia from 20th Century Glass, a comprehensive guide to all types of antique and collectible glass, with information, pictures and references. The Story of Glass Making in Canada from the Canadian Museum of Civilization. How Your Glassware is Made by George W. Waltz, February 1951, Popular Science.